You know, every time you stream a movie, pull up your GPS, or even just listen to music, you're actually interacting with mathematical ghosts. Seriously. So today, we're going to pull back the curtain and uncover the invisible 19th century math that, believe it or not, is the foundation for our entire digital world. And this all happened long before anyone even dreamed of a computer.
See, before we had code and silicon chips, processing information was, well, it was a physical, almost visceral thing. I want you to forget about abstract ones and zeros for a minute. Instead, picture a signal as a real, tangible force of nature, like a current surging through a wire, or the heavy turning of a brass gear. The algorithm wasn't some lines of code, it was the machine.
So yeah, a signal used to be a physical thing you could almost touch and feel. An electric current, a spinning shaft, the compression of airwaves from a sound. It was a messy, chaotic world of information. And this presented a massive challenge for the early scientists and engineers. How on earth do you pull a clean, precise meaning out of all that physical noise?
And that question brings us to our first giant, Carl Friedrich Gauss. He was obsessed with tackling the most fundamental problem of all, error. Back in the 17th and 18th centuries, scientists were pulling their hair out because no two measurements of, say, a star's position were ever exactly the same. The world was just too noisy.
Think about it. Every single measurement you could possibly take has some little bit of error baked into it. Maybe it's from a flicker in the atmosphere or a tiny imperfection in the telescope lens. While he was trying to predict the orbit of a new dwarf planet, Gauss decided to look at this problem not as an annoyance, but as a fascinating mathematical puzzle just waiting to be solved.
So what he came up with was the method of least squares, and here is his stroke of genius. Gauss realized that all those errors weren't just random, meaningless chaos. No, he had this incredible hunch that they followed a predictable pattern, what we now call the bell curve, or the Gaussian distribution. By figuring out the curve that best fit all that messy data, he could literally pinpoint the most probable true value hiding underneath.
And that's the key right there. Gauss treated every single observation as a two-part recipe. It was the true signal plus the noise. A star's position wasn't just its position, it was its true position plus all the atmospheric junk. A voltage reading was the real signal plus the instrument's tiny errors. And the whole point of math, he argued, was to strip away the noise and reveal the truth.
And what's wild is that this idea, this whole field of estimation theory, was so far ahead of its time that it pretty much sat on a shelf for over 100 years. It wasn't until World War II that it got dusted off to solve the very urgent, very real problem of how to shoot down enemy aircraft.
Okay, so Gauss gave us a way to handle random error. That's a huge step. But what about signals that aren't just noisy, but are also incredibly complex? That brings us to our next mathematician, Jean-Baptiste Joseph Fourier. He was staring at the complexity of the world itself and asking, how do you even begin to describe something like a complex sound mathematically?
While he was studying how heat flows through stuff, Fourier made this claim that was just absolutely mind-blowing at the time. He said that any continuous, repeating signal, and it doesn't matter how jagged or weirdly shaped it is, could be perfectly built just by adding together a bunch of simple, smooth sine waves.
Now, you have to understand, this was totally controversial. The big shots in the math world, including giants like Lagrange, they were not buying it. They thought, no way. How could you possibly create something with sharp, perfect corners, like a square wave, by just adding up a bunch of perfectly smooth, curvy waves? It just seemed impossible. But Fourier, he knew he was onto something. He showed them. If you start with one basic sine wave, and then you add a smaller, faster one on top of it, and then you add an even smaller, even faster one, and you just keep doing that over and over again, an infinite number of times, that sum of smooth waves magically sharpens up and becomes a perfect square wave.
The incredible tool he gave us, the Fourier transform, is basically a bridge between two different ways of looking at reality. There's the time domain, that's how a signal looks from one moment to the next. But then there's the frequency domain, and that's where you see its hidden recipe, exactly how much energy it has at every single frequency.
This changes everything. It means a complex sound like a chord on a piano or even the sound of your own voice isn't just one thing. It's a recipe, a mix of different frequency ingredients. And once you know the recipe, you can start messing with it. This is exactly what you're doing every time you use an audio equalizer. When you boost the bass or cut the treble, you're just changing the amounts of the ingredients in Fourier's recipe.
Alright, so we can handle noise and we can deconstruct complexity. But the real world has one more big problem for us. It is full of sudden, unpredictable shocks. You know, a lightning strike, a sudden gust of wind, the the simple flick of a switch. These aren't nice repeating waves. They're sudden, one-time events.
And this is where our third hero, Pierre-Simon Laplace, enters the story. See, Fourier's methods were amazing for things that were steady and repeating, but they were no help with urgent, practical questions like this one. If a bridge gets hit by a sudden, massive gust of wind, what happens next?
Laplace created a mathematical tool, a transform, that took Fourier's ideas and made them work for these sudden shocks. For the first time, his math let engineers predict, with scary accuracy, how a system would respond. Would it just absorb the shock and settle down? Would it wobble for a bit and then get stable? Or would it shake itself to pieces?
And that is why this matters so much. The Laplace transform became the absolute key to what we call stability analysis. It was the tool that finally allowed us to design all the feedback control systems and analog filters that keep everything from airplanes in the sky to our power grids on the ground stable and under control.
So let's just zoom out for a second and look at the big picture. What we've got here are three incredibly powerful mathematical ideas, all born in the 19th century, way before the technology even existed to really use them.
It's a beautiful story, really.
First, Gauss taught us how to find the truth hiding in the noise. Then Fourier gave us the recipe to deconstruct any complex thing into its simple parts. And finally, Laplace gave us the tools to predict how systems react to sudden shocks. Together, these three ideas built the foundation for all modern signal processing.
And if there is one thing you take away from all this, let it be this. The theories that make your smartphone work, that make your Wi-Fi connect, that even power modern AI, they weren't born in Silicon Valley. They were forged in the minds of these 19th century mathematicians who were just trying to make sense of the physical, messy, analog world around them.
Imagine, for a second, an internet that could connect continents, but every single message you sent arrived as total gibberish. I'm not kidding. That was the reality for the Victorian internet, the very first transatlantic telegraph cables. A brilliant idea was on the brink of complete failure, all because of this one mysterious problem that turned crisp, clear messages into an unintelligible smear. So let's dive into how they cracked one of the greatest puzzles of the era.
You see, back in the mid-19th century, over land and across shorter distances, the telegraph was an absolute miracle. The signals were sharp, they were clear, and they were pretty much instantaneous.
The whole system worked like a charm because it was so precise. A quick pulse of current meant a dot. A slightly longer one, that was a dash. The message you sent was exactly the message that was received. Perfect.
But when they tried to stretch that cable for thousands of miles along the dark, cold ocean floor, everything changed. A problem that literally no one had seen coming popped up, and the simple physics that made the telegraph work started to completely break down.
Instead of a nice, sharp click arriving on the other side, the signal showed up as this long, slurred, lazy rise in current. They called it retardation, and it was a disaster. It blurred all the dots and dashes together, threatening to bankrupt the entire, incredibly audacious project.
So this crisis naturally led to a huge fight, a real clash of titans. And the debate over how to fix this signal smear boiled down to two totally opposite ideas. Should they just hit the signal harder, or should they try to listen more closely?
And this is where a guy named William Thomson, you might know him as Lord Kelvin, had a stroke of genius. He figured out the cable itself was the problem. It was acting like a massive capacitor. Think about it. You've got the copper wire on the inside, the seawater on the outside, and the insulation in between. Before any signal could actually get through, you had to basically fill up the entire 2,000-mile cable with electricity.
Okay, so this led to a major showdown. On one side, you had the project's chief electrician, a man named Wildman Whitehouse. His solution? Pure brute force. Just blast the cable with thousands of volts, like trying to clear a clogged pipe with a fire hose. But Thomson, he argued for finesse. He said, look, the information is still in there. Inside that smear, you just need a detector that's sensitive enough to actually read it.
And the result? Well, it was both a tragedy and a total vindication. Whitehouse's high-voltage blast literally fried the cable's insulation, completely destroying it. But in the few weeks that it actually worked, they managed to send a message from Queen Victoria. It took 16 hours to send just 98 words, but it proved Thomson was right all along. Low power and high sensitivity was the only way it was ever going to work.
But here's the thing. Thomson's fix was really just a patch. Solving the smear problem only revealed an even deeper mystery about how electricity really works. And the person who would solve that was a reclusive, pretty eccentric genius named Oliver Heaviside.
Now, Heaviside, he completely changed the game. While Thomson saw the signal kind of like heat spreading through a pipe, a process called diffusion, Heaviside saw it for what it truly was, an electromagnetic wave. He looked at the whole picture, taking into account not just resistance and capacitance, but two other crucial factors, inductance and leakage. This was a total paradigm shift.
And because he was looking at the full picture, he stumbled upon a solution. A solution so deeply counterintuitive, it was almost unbelievable.
So, to get this, we have to talk about something called inductance. You can think of it like electrical inertia. It's a property that resists changes in the current. And for decades, every engineer on the planet saw inductance as just another enemy, another form of resistance they had to fight against.
But Heaviside discovered the exact opposite. This is the big twist. Inductance wasn't the problem at all. It was the solution. The very thing everyone thought was messing up the signal was, in fact, the key to making it perfect. Just incredible.
And he boiled it down to this, just beautifully elegant formula. He proved that if you could perfectly balance the magnetic field properties, that's the inductance and resistance, with the electric field properties, the capacitance and leakage, you would create a distortionless line. Every frequency of the signal would travel at the exact same speed, and the message would arrive perfectly preserved.
Now, Heaviside was a pure science guy. He published his theory, but he never patented a device to actually do it. So for decades, turning this elegant equation into a real-world product, well, that became a million-dollar race.
And that's when Michael Pupin, a physicist over at Columbia University, enters the story. He did what Heaviside didn't. He figured out the precise, practical engineering. He patented a method for adding these things called loading coils, which are basically just clumps of inductance, at very specific, carefully calculated intervals along the wire. This was the practical blueprint the industry had been waiting for. And was it valuable? Oh, you bet. AT&T, who was desperate to build a long-distance telephone network, immediately paid Pupin a staggering $455,000 for his patent. Now, to put that into perspective for you, we're talking about over $11 million in today's money, an absolutely incredible sum for a single idea. But for AT&T, the return on that investment was just astronomical. The company saved an estimated $100 million in the first quarter of the 20th century alone. These little coils completely revolutionized the economics of communication.
So, what is this whole 50-year journey, from a mysterious smear in the ocean to a $1 million patent, really tell us about how things get invented?
Well, it shows that progress is rarely a single eureka moment, you know? It took decades to go from Thomson just figuring out the problem, to Heaviside discovering the theoretical cure, and then, finally, to Pupin engineering the actual device that allowed clear voices to travel between cities.
And this, right here, is the crucial takeaway. World-changing innovation, it's a team sport. It almost always requires the pure scientist, the theorist like Heaviside, to uncover the fundamental principles. But then it needs the practical engineer, like Pupin, to turn that theory into a useful invention. And finally, it needs the capital from companies like AT&T to scale that invention and bring it to everyone.
Think about it. The year is 1915. There are no satellites, no fiber optics, none of that. So how could a human voice, just a tiny electrical pulse, possibly survive a journey of over 3,000 miles from New York to San Francisco without just fizzling out? To answer that, we have to go back and understand the one huge problem that every single early inventor was stuck on. Before you could send a message anywhere far, you first had to solve the problem of silence, the simple fact that every signal eventually dies. Yeah, see, this was the reality of what historians call the passive era. Back then, engineers had clever ways to shape a signal or filter it, but what they could not do was add new energy to it. And that meant, over any real distance, every message, every single one, just faded away into the background static. Gone. And this comparison right here, it says it all, doesn't it? On one side, you have the passive era, where distance was the ultimate bad guy. On the other side, you've got this new active era, where a signal could be reborn over and over again. So the big question is, what changed? What made that incredible leap possible? Well, the breakthrough, it came from this incredible device that could act like a valve. But not a valve for water, No, this was a valve for electricity itself. And this was the invention of the amplifier. So back in 1906, this inventor, Lee DeForest, he comes up with this thing called the Audion triode. Now at first, it was kind of weird, pretty unreliable, but it held the secret to solving the problem of distance forever. So how in the world did this valve actually work? It's honestly genius, and it's simpler than you might think. Picture this, a tiny, weak signal from a voice comes in. That weak signal is just strong enough to control the flow of a much more powerful stream of electricity. So the little signal is basically opening and closing this giant valve, creating a perfect, beefed-up copy of itself on the other side. But you know, the story wasn't that simple. The funny thing is, DeForest himself didn't fully understand why his invention worked. It actually took these brilliant research teams at Bell Labs and GE to really perfect it. They're the ones who turned this mysterious, kind of flaky device into a stable, high vacuum tube that you could actually count on. Okay, so they have this amazing new technology. What do they do with it? Well, with a reliable amplifier finally in their toolkit, engineers got really ambitious. They were ready to try something that sounded like science fiction, sending a voice clear across the entire American continent. And that brings us to the year 1915. This is the moment it all comes together. This is the answer to that very first question we asked. What AT&T did was they took these new vacuum tube amplifiers, they called them repeaters, and they installed them all along the telephone line. The idea was simple but brilliant. Every few hundred miles, right when the signal was getting tired and starting to fade out, a repeater would catch it, make a brand new, powerful copy, and shoot it down the line, totally fresh and clear. I mean, the pace of this stuff was just breathtaking. In less than 10 years, we went from being limited by a few miles of wire to spanning a whole continent. But you know how it goes, right? You solve one massive problem, and it immediately creates a brand new one. See, beating distance was a huge win, but actually building a network for everybody, that was a whole different ballgame. The new bottleneck wasn't about the laws of physics anymore. No, it was about economics. So that leads us to the next big question. It's awesome that a voice can travel 3,000 miles, but who cares if you have to run a whole new, super expensive copper wire for every single phone call happening at the same time? That's just not gonna work. It's not scalable. And the reason this was so ridiculously wasteful is this. A human voice only uses a tiny little slice of a copper wire's total capacity, what we call its bandwidth. So all that extra potential on the wire, it was just sitting there doing absolutely nothing, totally wasted. But of course, they came up with a solution, and honestly, it was beautiful. So incredibly clever. The idea was called multiplexing, which is really just a fancy way of saying they figured out how to slice and dice the available space on that one single wire. The technique is called frequency division multiplexing, and the best way to get it is to imagine that wire is a giant highway. Before, you had one car, one phone call taking up the entire road. FDM was like painting lanes on that highway. All of a sudden, you could have dozens of calls all traveling together at the same time, each staying perfectly in its own lane. And here's how they did it, which is so cool. The engineers used that same vacuum tube in a new way, as something called an oscillator. They used it to shift each different phone call onto its own unique frequency, its own lane on the highway. Then they could just stack them all up and send them all down the same wire on their long journey. But there was a catch. Of course there was. For any of this to work, you had to be able to pull all those conversations apart perfectly at the other end. If you couldn't, you'd get what they called crosstalk. Hearing bits of someone else's conversation bleeding into your call. The system needed flawless lane discipline. And this challenge required a whole new level of precision, which led to the theory of the wave filter. So, the first key concept is the passband. Just think of that as the one lane of traffic, the specific frequency that you want to let through. And then you have the stop band. That's everything else. All the other lanes, all the other conversations, everything you need to block out completely. You needed a perfect bouncer at the door that only lets your conversation in. And the engineers who designed these things, they were absolute wizards. They used some seriously complex math to build filters that weren't just good, no way. They were described as being like brick walls in the frequency domain. That's how sharp the separation was between each channel. Just unbelievable precision. And that's it. That is what truly built our modern network. First, the amplifier gave us distance. Then, the filter gave us capacity. Together, these two technologies became the silent sentinels of the network, taking the potential chaos of millions of voices and sorting it all into perfect, orderly lanes of traffic. Imagine you're on the coast of England during World War II. It's dark, it's foggy, and you know that somewhere out there an enemy air raid is coming, but you can't see a thing. The clouds, the night, they're the enemy's best allies. So how on earth do you defend a nation when you're completely flying blind? Well, the answer to that question would lead to some of the most brilliant, most creative engineering of the entire 20th century. You know, before the war, signal processing was something, well, commercial. It was all about getting a clearer radio show or a better phone call. But suddenly, in the 1940s, it wasn't about convenience anymore. It was about life and death. The ability to pull a tiny, faint signal out of the noise wasn't just a neat trick, it was literally a matter of national survival. So, before radar became the go-to solution we know today, the British tried something else. Something massive, almost unbelievable. They decided to listen for the enemy. And this set up an incredible race against the one thing they couldn't beat, the fundamental speed of sound itself. And when I say massive, I mean it. Look at these things. They're not just big microphones. We're talking about colossal concrete structures, some of them 30 feet tall, shaped like huge parabolic dishes. They were basically acoustic telescopes designed to scoop up the faint hum of enemy bomber engines from all the way across the English Channel and focus all that sound down to a single point where an operator could hear it. But here's where the whole brilliant idea just fell apart. It's a simple math problem. Sound travels at about 340 meters a second. By the late 1930s, bombers were getting fast, approaching half that speed. So think about it. By the time the sound of that plane traveled all the way across the channel and reached the giant concrete ear, the plane itself had already flown for miles. You are always listening to where the enemy used to be. The system was basically obsolete before they even finished building it. Okay, so sound was way too slow. The next logical step, use radio waves. They travel at the speed of light, which solves the time delay problem instantly. This is where radar comes in. So problem solved, right? Well, not quite. Radar got rid of this speed problem, but it came with two of its own, brand new flaws. Flaws so bad they nearly made the whole system useless. The first huge challenge was the echo itself. I mean, the signal you send out is powerful, but the piece that bounces off a distant airplane and comes all the way back is unbelievably faint. Trying to pick that out was like trying to hear a single person whisper in the middle of a roaring stadium. The signal was there, somewhere, but it was just completely buried in noise. This all comes down to what engineers call the signal-to-noise ratio, or SNR. For an early radar operator, all that noise just looked like a jagged, messy line of static on their screen. They actually called it grass. And the plane's echo? That was just one tiny little blip that barely poked its head above that grass for a split second. Imagine staring at that for hours trying to find it. It was a massive strain. But the second problem was in many ways even worse, because the noise wasn't just random static. Your powerful radar signal doesn't just bounce off the plane, it bounces off of everything. And let me tell you, the echo you get back from a giant mountain is 1,000,000 times stronger than the one you get from a little airplane. This is what's known as clutter. A big clutter signal from a nearby cliff face or even a rough sea could totally overwhelm the radar receiver. It would just blind it in that direction. A whole squadron of planes could be flying right there, but their tiny echoes would be completely invisible, lost in the massive radar reflection of a nearby hill. So we've got two huge problems, right? A signal that's too weak to find in the noise, and a signal that's totally hidden by clutter. Let's deal with the noise problem first. The solution here didn't come from building a bigger, more powerful antenna. It came from a truly revolutionary piece of mathematics. It all started in a classified report from 1943. A researcher at RCA Labs named Dwight North asked a really simple but totally profound question. What is the absolute best, the most mathematically perfect way to design a receiver to find a signal you already know the shape of when it's buried in random noise? And his answer? It changed everything. See, the big idea, the huge mental shift, was this. Stop looking for just any blip of energy. That's super inefficient. North realized that the radar sends out a pulse with a very specific, known shape. So, he argued, the receiver should be designed to look for that exact shape, and only that shape. It's like having a key that's designed for one very specific lock. This is how it works, and it's so elegant. You can think of it like a template matcher. The radar knows the exact shape of the pulse it sent out, so it uses that shape as a kind of mathematical template. It then slides that template across the noisy, messy signal that comes back. And for most of that signal, nothing happens. But when the template slides over the faint, hidden echo of the plane, bam, it's a perfect match. The output of the filter spikes way up. Target detected. It was math, pure math that could finally pull that whisper out of the roar. All right, so the matched filter solved the noise problem. That's one down. But what about the clutter? The mountains and the cliffs are still there, totally blinding the radar. The solution to this problem, well, it wasn't just math. It was a piece of physical engineering so bizarre it honestly sounds like something out of a sci-fi novel. It required them to build a memory out of liquid metal. The technique is called moving target indication, or MTI. The physics behind it is that a stationary object, like that mountain, is going to return the exact same radar echo, pulse after pulse after pulse. But a moving object, like a plane, is going to return an echo that's just slightly shifted. But to spot that tiny, tiny difference, the radar needed something that didn't exist in the 1940s. It needed a way to store one entire radar pulse so it could compare it to the next one. It needed memory. So how do you build computer memory in an age of vacuum tubes long before silicon chips were even a dream? Well, you build a mercury delay line. I'm serious. It was literally a long tube filled with liquid mercury with a crystal at each end. This was their version of RAM, and it was built out of a toxic liquid metal. And the genius of the system is just incredible. Here's how it worked. The first radar echo, let's call it pulse 1, comes in. It gets converted from an electrical signal into a sound wave, which then starts traveling slowly down the tube of mercury. They made the tube the perfect length so that just as that sound wave gets to the other end, the very next radar echo, pulse 2, arrives live from the antenna. Then the system does something simple. It subtracts the old, delayed pulse 1 from the brand new pulse 2. So what happens when you subtract them? Well, the echo from the mountain in pulse 2 is identical to the echo from the mountain in pulse 1. So mountain minus mountain equals 0. It just vanishes. But the plane has moved, so its echo in pulse 2 is different from its echo in pulse 1. When you do the subtraction, it doesn't cancel out, it leaves a signal. The stationary clutter disappears, and suddenly the moving target pops out, clear as day. It is just an absolutely brilliant, almost poetic system. These two breakthroughs, the matched filter from math and the delay line canceller from physics, were absolutely critical to the Allied victory. But their story doesn't end there. Their legacy goes so far beyond the war, and they actually laid the groundwork for the digital world that you and I are living in right now. You know that matched filter, the idea of looking for a known signal in noise? That is a fundamental cornerstone of pretty much all modern digital communication. It's how your phone, your Wi-Fi, your GPS, how they all pull a clean, clear signal out of an incredibly noisy world. And moving target indication, that's a standard feature in every single modern radar, from air traffic control systems to the weather radar you see on the news. These incredible analog wartime inventions became the bedrock concepts of our digital age. We're going to unpack how the desperate life-or-death problem of shooting down enemy planes led to a report that, well, basically invented the future as we know it. It's a wild ride. All right, so to really get this, you got to put yourself in the shoes of an anti-aircraft gunner during the war. You see this tiny speck in the sky, and it's screaming towards you at hundreds of miles an hour. You've got, what, maybe 3 seconds? 3 seconds to figure out not where it is, but where it's going to be by the time your shell gets up there. And if you're wrong, well, the stakes couldn't be higher. It's not just a math problem, it's a real-time computational nightmare with lives on the line. So here's how we're going to break this down. First, we'll look at the physics of the impossible shot. Then, we'll check out the amazing electronic brain they built for guns. After that, we dive into the legendary Yellow Peril report. And finally, we'll see how this all led from control systems to a whole new science called cybernetics. Okay, let's really get into the weeds of this problem. The core challenge, right, is that you're not aiming where the plane is. You're aiming where it's gonna be. You're trying to predict the future, a future that's just a few seconds away, but it's in three-dimensional space. You've got to account for its speed, its direction, its altitude, not to mention the arc of your own shell. At its heart, this is a pure prediction problem. And you know what the language of prediction is? It's math. Specifically, something called differential equations. Now don't worry, we're not going to do a pop quiz. All you need to know is that these are the equations that describe how things change over time. And for these gunners, it meant their weapon had to solve these super complex equations, not with a pencil and paper, but right there in the heat of the moment. instantly. So how in the world do you solve a math problem that complex, that fast? Well, the first big breakthrough came from a place you might know, Bell Labs. They created this thing called the M9 gun director. And let me tell you, this was not just a fancy gun sight. This was one of the very first electronic analog computers, a literal electronic brain built for one single deadly purpose. And this was a huge leap in thinking. I mean, before the M9, these kinds of prediction machines were all mechanical. Think of these incredibly complex clocks just filled with whirring gears and cams. The M9 just threw that whole idea out the window. Instead of gears, it used electricity. The math was literally modeled by the flow of voltage through its circuits. So data like the plane's altitude or its speed, that became a specific voltage. The whole calculation was happening at the speed of light, not the speed of grinding metal. It was a total game changer.
So here's how this whole thing worked. It was this beautiful, seamless loop. First, radar locks onto the plane. Instantly, the M9 turns that radar data into electrical voltages. Then its vacuum tubes, the brain of the operation, do all of the calculus to predict exactly where that plane is going to be. And finally, it sends a jolt of electricity to motors that physically move the gun to the perfect spot. It was this perfect loop: sense, calculate, act. All of it happening in the blink of an eye.
So, did it work? Oh, you better believe it worked. It was incredibly effective. When the V1 flying bombs, the so-called doodlebugs, were attacking London, the batteries using the M9 were knocking down over 90% of them. 90%. It was an absolute triumph, but there was a catch. It worked perfectly against a target that flew in a straight, predictable line. So what happens when the target is a human pilot who starts to fight back? And this is where the story gets really interesting. See, the M9 was a genius, but it was a very specific kind of genius. It was great at solving what we call deterministic problems with a single, predictable answer. But you put it up against a human pilot who's ducking and weaving and doing everything they can not to be predictable, suddenly the M9 was completely lost. They needed a whole new way to think about the problem. And that new thinking came from this brilliant MIT mathematician, a guy named Norbert Wiener. And his big idea was, well, it was revolutionary. He basically said, stop trying to predict the pilot's exact path. You're never going to get it. A human isn't a perfect equation, but they're not totally random either. He saw the pilot's movements as what he called a statistical time series. Basically, a stream of data that looks messy but has hidden patterns. You can't be 100% certain of their next move, but you can calculate the probabilities. So Wiener wrote all of this down in a classified report back in 1942. Now, the official title was super dry and boring, but everyone started calling it by its nickname, the Yellow Peril. Why? Well, two reasons. One, it had this bright yellow cover, and two, the math inside was so incredibly dense and difficult that most engineers at the time just couldn't make heads or tails of it. It was, to them, a peril. And what was inside that report was a complete paradigm shift. I mean, think of it as two totally different ways of seeing the world. On one hand, you have the M9's world. It's clean, it's deterministic, it assumes a perfect, predictable flight path. But then you have Wiener's world, which is messy, it's probabilistic. He had this brilliant idea to treat the pilot's zigzagging not as random chaos, but as noise that's messing up the signal of the plane's general direction. And with that one idea, the whole problem changed. It wasn't about physics anymore, it was about information. The new question was, how do you filter the signal from the noise? Now, as it turned out, Wiener's ideas were a little too ahead of their time to be fully built into a machine before the war ended. But the concepts inside that Yellow Peril report, they were about to explode out of the military and change, well, pretty much everything. A brand new science was about to be born. And this was the big one, the earth-shattering aha moment. Wiener realized that the math he was using to describe this feedback loop of a gun and a radar system, communication, control, correction, was basically the exact same math that describes how our own nervous systems work. He found a universal language that connected the world of machines with the world of biology. And so this new, grand, unified science needed a name. He called it cybernetics. It's the science of communication and control systems, whether you're talking about a machine or a living thing. It's all about how systems use feedback to steer themselves and stay on course. It was a completely new lens through which to see the world.
And the legacy of that one yellow report is just staggering. The methods Wiener came up with for filtering a signal from noise became the bedrock of modern technology. That core idea, it's what allows your cell phone to get a clear signal. It's literally what let the Kalman filters guide the Apollo missions to the moon. It's inside almost every control system you can think of. And yeah, it is the direct ancestor of the predictive algorithms that are the foundation of modern AI.
All right, today we're talking about something really cool, the mechanical brains. We're going to take a trip back in time to an era way before silicon and software, when computation was this physical thing you could literally see and touch.
So let's kick things off with a big question. How do you even compute something without circuits or code? I mean, in our world of smartphones and laptops, that sounds kind of impossible, right? But what if a computer wasn't some abstract box? What if it was a machine that literally modeled the problem it was trying to solve?
Well, that's the whole idea behind an analog computer. It's a machine that uses a physical analogy, gears, pulleys, shafts, the rotation of a disk to represent and solve a problem. Think about that for a second. It's not running a program, the machine is the program.
Okay, so to really get our heads around this, we need to rewind the clock. We're going back to a time before the digital dawn, when these incredibly intricate machines were the absolute pinnacle of technology for solving the world's toughest problems.
And they were absolute workhorses. These mechanical brains were doing all the heavy lifting for signal processing and complex math long before the first transistor was ever even a thought. So let's jump in and look at a couple of the most brilliant examples.
First up, we've got Lord Kelvin's incredible tide predicting machine. And this thing is from all the way back in the 1870s. It is just such an elegant and beautiful solution to a massive natural problem. So what was the big problem that was built to solve? Predicting tides. Now, that might not sound super complicated, but trust me, it is. Tides are insanely complex. You've got the moon pulling on the ocean, you've got the sun pulling on it, all these different forces creating these overlapping waves, or harmonics. It's a total mathematical nightmare to figure out by hand. And for any big port, getting this wrong was a dangerous and very expensive mistake.
So how did this thing work? Well, it was basically a mechanical synthesizer for waves. Okay, so check this out. Each one of those pulleys you see was designed to move up and down, right? And each one mimics the frequency of a specific tidal force. One for the moon, another for the sun, and so on. Then they ran this single long wire over all of them. As the pulleys bobbed up and down, the wire physically, literally, added up all of those movements. And that final, combined motion, it drove a pen that drew the future tide curve onto a spinning piece of paper.
And that's the mind-blowing part, right? The machine processed all these complex signals by literally adding them together with steel and wire. It wasn't calculating numbers in an abstract way, it was physically becoming the calculation. Just pure mechanical genius.
Okay, so that was amazing, but things got even bigger and more complex. Let's fast forward to the 1930s at MIT with a guy named Vannevar Bush. He created an even more powerful mechanical brain, the differential analyzer, built for math that was just too big to solve by hand.
So now the challenge is even bigger, solving differential equations.
And if it's been a while since your math class, just know these are the equations that describe, well, pretty much everything in the physical world. How electricity flows, how air moves over a wing, all that stuff. And Bush's machine? It was this room-sized monster built to wrestle with that very math. And at the very heart of this beast was this one critical component, the ball and disc integrator. This little gadget was the key. It's the part that could actually do calculus mechanically. Here's the gist of how it worked. You have this big, flat disk, and it's spinning. The speed it spins at represents something like, say, time. Then you have this little steel ball resting on top of it, and where you place that ball, how far from the center, that represents the function you're trying to figure out. It's like you're building the math problem out of metal.
So as the disk spins, the ball spins, and that ball makes an output cylinder turn. And get this, the total amount that output cylinder has rotated is the answer. It's the solution to your integration problem, right there in physical rotations. No ones and zeros, just motion.
Okay, but hold on a second. If you're thinking like an engineer, you might spot a problem here. The force from a tiny little ball rolling on a disk, that's practically nothing, right? So how on earth could that tiny bit of force be strong enough to turn all the heavy gears and shafts that come next in the machine? The short answer, it couldn't. It would just slip and be totally useless.
And the solution to this problem, well, it wasn't just clever. It was a flat-out engineering miracle that made the whole thing work.
That miracle was called the torque amplifier.
This thing was the secret sauce, the ingenious hack that solved the whole weak force problem.
So the idea is actually a lot like how a winch on a ship works. You know how you can pull a huge, heavy ship to the dock just by wrapping a rope around a spinning drum? It's the same principle. That super weak input from the little ball just slightly tightens a string wrapped around a powerful, constantly spinning drum. That little bit of friction is all it takes for the string to grab hold and harness the massive power of the drum. It literally amplifies a tiny whisper of force into a powerful roar, strong enough to drive the rest of the machine. So as brilliant as this machine was, it was, well, let's just say it was a temperamental beast. Let's talk about its legacy, but also its very real-world flaws.
And you have to understand, this thing was the supercomputer of its time. It did incredibly important work. We're talking calculating ballistics tables for the Army in World War II. I mean, getting shells to land where they're supposed to. It mapped out how radar waves travel for the MIT Radiation Lab, which was crucial for the war effort. This machine was a big deal.
But programming this thing, well, it wasn't about typing code. It was about grabbing your wrenches and screwdrivers. You'd spend days physically taking it apart and putting it back together, rerouting shafts and swapping out gears to set up a new problem. It was a greasy, hands-on, totally manual job.
And in the end, its biggest weakness was that it was, well, physical. Its precision was limited by real-world stuff. The little balls could slip just a tiny bit, the gears could wear down, the strings on those torque amplifiers could stretch. These weren't software bugs you could patch, they were fundamental limits of the materials themselves.
But even with those limitations, its legacy is just profound. What this machine proved, what it really demonstrated to the world, was that computation wasn't some abstract idea. It was a physical process. You could build a machine that could actually simulate the fundamental differential equations of the universe.
So what do a Hollywood movie star and a 55-ton machine have in common? I know, it sounds like a bad joke, right? But the answer is kinda mind-blowing. They both secretly laid the foundation for your smartphone, your Wi-Fi, and pretty much every secure call you've ever made. Let's get into it. Alright, so our first story kicks off with a massive problem. You've got Allied leaders, right? Churchill and Roosevelt. They need to talk strategy, but they're separated by an ocean crawling with enemy spies listening in on every radio wave. How do you have a truly secret conversation?
Well, the Allies' answer was this incredible piece of technology, a top-secret system they called Sig Sally. And look, this wasn't some little handheld scrambler. This thing was a massive undertaking, a true beast of a machine.
And when I say beast, I am not kidding. This machine was an absolute behemoth. It weighed 55 tons, it took up an entire huge room, and it ran on thousands and thousands of fragile vacuum tubes. This was the brute force approach to secure communication for sure.
So how the heck did this monster work? Well, in a nutshell, Sig Sally did something that was totally revolutionary for its time. It took the smooth, analog wave of a person's voice and basically chopped it up into digital blocks. Then, it scrambled those blocks with a random key of pure noise, making it total gibberish to anyone listening. And on the other end, another machine put it all back together perfectly. Now, this whole process of turning sound into digital bits, it actually has a name, pulse code modulation, or PCM. And this is the key. This was the first time it was ever practically used. It is the granddaddy of all digital audio today. I mean, every Spotify track, every phone call, every podcast, it all owes a little something to this giant wartime machine.
And here's a cool little detail. If you were an eavesdropper, all you heard was static. But for the actual users, Churchill and Roosevelt, they heard this weird, distinct buzzing sound from the machine's control tones. And because of that sound, the whole top-secret system got this awesome nickname, the Green Hornet. Okay, so while the military is busy building this gigantic machine to protect the content of the message, a totally different idea was brewing in a very, very different place. This idea wasn't about scrambling the message itself. It was about making the path it traveled on impossible to follow. So, in 1941, you get maybe the most unlikely inventing team in history. Hedy Lamarr, one of the biggest movie stars in Hollywood, and George Antheil, a cutting-edge composer. And their goal? To figure out how to stop the enemy from jamming the radio signals that were supposed to guide Allied torpedoes to their targets. And their solution was just, well, it was beautiful. It was called frequency hopping. The idea was to have the radio transmitter and the receiver constantly jump from one frequency to another in a synchronized, random-looking pattern. So if an enemy tried to listen in or jam the signal, all they'd get would be these little unpredictable blips of noise. The signal itself would be almost impossible to catch.
But wait,
How do you keep the transmitter and the torpedo perfectly in sync as they're hopping around? Well, the inspiration for this was just genius, and it came from Anthal's work with player pianos. They figured they could use two identical player piano rolls to coordinate the frequency jumps across 88 different channels. Yep, the exact same number of keys on a piano.
So now we've got these two wild, incredibly different approaches on the table. One is this huge government project, and the other is a clever idea cooked up in Hollywood. Let's put them side by side and see what happened next.
I mean, this table just lays it all out, doesn't it? Sig Sally was all about protecting the content, using digitization. Frequency hopping was about protecting the path the signal traveled. One was built by military engineers and got used right away, and the other, invented by these outsiders, was flat out rejected by the Navy at the time.
So yeah, the Navy looked at the whole player piano idea and said, thanks, but no thanks. This is too clunky to stick in the torpedo. But here's the thing about a truly brilliant idea. It doesn't just die. Decades later, once the transistor was invented and everything got smaller and more reliable, this concept of frequency hopping was brought back to life, and boy, did it ever become a cornerstone of modern tech.
So that brings us to the big question. How did these two completely separate, secret projects from the 1940s, one that was a huge success at the time and one that was basically a failure, how did they both end up shaping the digital world that we all live in today?
It's really amazing when you think about it. These two inventions became like the twin pillars of our digital world. Sig Sally's method of digitizing voice, that's the direct ancestor of every secure phone call and every VoIP system like Zoom or Skype. And Hedy Lamarr's frequency hopping, well, that's the fundamental principle that makes your Bluetooth headphones and your home Wi-Fi network even possible. One secured what we say, and the other secured how we send it.
So you've got these two worlds that just seem like they shouldn't be able to talk to each other. First, there's our world, the analog world. Think of a sound wave or a ray of light. It's continuous, it's infinitely detailed, and let's be honest, it's kind of messy. Then you have the digital world. It's the complete opposite. It's built on separate, countable things. Zeros and ones, it's all structure and perfect order. They seem totally incompatible.
And that brings us to the big question, right? If you're gonna chop up a smooth, continuous reality into a bunch of separate little numbers, what happens to everything that falls in between your measurements? Does it just vanish? Poof, gone forever? This was a massive hurdle.
Well, the answer starts to take shape way back in the 1940s with a truly brilliant mathematician named Claude Shannon. His work basically laid the foundation for, well, everything that came next.
See, back then, the world was completely analog. Imagine making a long-distance phone call. The electrical signal carrying your voice down that wire was your voice, literally. And as it traveled, it picked up all this static and hiss. That noise got baked right into the message itself, and there was absolutely no way to clean it up. The farther it went, the worse it got.
This was Shannon's genius move. He just looked at the problem in a totally new way. He realized that information wasn't some fuzzy, abstract idea. No, he said it's a physical thing, something you can actually measure and count just like weight or temperature. He basically wrote the rule book for information itself.
And this all culminated in his masterpiece, information theory. The killer idea here is that you can separate the message from the thing carrying it. By turning your message into a code, a string of symbols like bits, you could send it down a really noisy, crackly phone line. And then, with the right math, you could put it back together perfectly on the other side, with zero errors. This idea was a complete game changer.
Okay, so the theory is brilliant, but there's still a huge practical problem on the table. How do you even capture that messy real-world signal to turn it into code in the first place? Well, the answer feels a little bit like magic. It's what's known as the sampling miracle. Let's get right back to our big question, but let's make it really specific. Imagine you measure a sound wave at one exact moment, and then the next exact moment. What about all the infinite little wiggles and waves that happened in between? The common sense of the time said, yep, that's gone, lost forever. But it turns out, common sense was about to get completely turned on its head.
The answer has a fancy name: the Nyquist-Shannon sampling theorem. Shannon, building on some earlier work by Harry Nyquist, proved something that felt and still feels like a mathematical miracle. He showed that you can take a handful of separate, discrete measurements and use them to perfectly reconstruct the original, continuous, infinitely detailed signal. No information loss. None. But only if you follow one very, very specific rule.
And this is the rule. It's so simple, it's almost hard to believe. Your sampling rate, that is, how often you take a measurement has to be more than double the highest frequency in the signal you're trying to capture. That's it. What this proves mathematically is that the spaces between the samples don't actually contain any new information you don't already have, as long as you're sampling fast enough. It's incredible.
So let's make this real. How does this actually work? Well, the human ear can generally hear frequencies up to about 20,000 hertz. So if we follow the rule, we need to sample at a rate greater than 2 times that, so more than 40,000 hertz. And guess what? This is exactly why the standard for CD audio was set at 44,100 hertz. It's not a random number. It's the rate that guarantees a mathematically perfect digital copy of every single sound a person can possibly hear.
And you can't overstate how huge this was. This wasn't just some neat theory. This was the mathematical permission slip engineers needed. It gave them the confidence to say, okay, we can do this. We can abandon analog and build our world on digital, knowing for a fact that they wouldn't lose anything important in the process.
But there's a catch, a big one. That beautiful promise of perfect reconstruction comes with a very serious warning. If you break the rule, if you don't sample fast enough, really bad things happen. You get a bizarre and dangerous distortion called aliasing.
Aliasing is, well, it's like a ghost in the machine. When you sample too slowly, the high-frequency information you're missing doesn't just go away. Instead, it gets misinterpreted. It folds over and disguises itself as a brand new, fake, lower-frequency signal that wasn't there in the first place. It's a phantom signal that pollutes your data. Okay, the absolute best way to get your head around this is with something you've definitely seen 100 times. Think about an old movie. A movie camera is just a sampling device, right? It's taking snapshots or samples of reality, usually about 24 times every second. Now, picture a wagon wheel in a Western, and it's spinning like crazy. The speed of that spin is a very high frequency. If it's spinning too fast for the camera's 24 frames per second sample rate, well, the camera just can't keep up. It is, by definition, undersampling the motion of that wheel. And what do you see? You know it! The wheel looks like it's standing perfectly still, or even weirder, spinning slowly backward. That backward motion? It's not real. It's a total illusion. It's a fake, low-frequency signal created by aliasing. That is a perfect picture of what happens to your audio or your data when you break the sampling rule. So at the end of the day, it all boils down to this. It's a simple choice with massive consequences. You sample above that critical rate, the Nyquist rate, and what you get is a perfect reconstruction. That's your high-fidelity CD audio. But if you sample below it, you get aliasing. You get that dangerous distortion, the wagon wheel effect. This is the fundamental trade-off at the heart of every single digital conversion.
So, how did we get from these groundbreaking ideas in the 1940s to, well, everything we use today? This whole journey of processing signals can really be broken down into 3 big eras. You can think of it in 3 chapters. First was the hardware-defined era, where if you wanted something done, you literally had to wire its function into a physical circuit. Then, around the 80s, we jumped into the software-defined era. Now, powerful little computer chips could do the heavy lifting by running clever algorithms. And that brings us to today and the start of the data-defined era. This is where AI, neural networks, are basically teaching themselves how to interpret signals in ways we never even explicitly programmed them to.
All right, we're about to dive into the story of an algorithm that, well, it quietly changed everything. It's the mathematical key that really unlocked our entire digital reality. This is the story of the FFT revolution.
So get this, what if I told you there's a secret piece of math written down when Napoleon was still around that was basically lost for over 160 years, only to be rediscovered and become the hidden engine behind, military radar, Wi-Fi, even medical imaging? Sounds crazy, right? So what is this thing? And how in the world did it solve what was thought to be an impossible problem?
To really get the genius of the solution, first, you have to understand the massive wall that stood in its way. For decades, the whole idea of true digital signal processing was pretty much just a dream, stuck behind this huge computational bottleneck. At the very heart of this problem was something called the discrete Fourier transform, or the DFT. The easiest way to think about it is like a mathematical prism. It takes a really complex signal, say a sound wave or a radio wave, and it breaks it down into all the simple, pure frequencies that it's made of.
See, there are 2 different ways you can look at a signal. In what's called the time domain, you're just seeing its strength go up and down from one moment to the next. But the DFT, it flips the script. It lets us see that same signal in the frequency domain, which reveals its unique fingerprint,
that specific mix of pure sine waves that makes it what it is.
But, and this is a huge but, here was its fatal flaw. The DFT was just computationally brutal. To analyze a signal with n data points, a computer needed to do n² operations. Think about that. If you double the detail of the signal, you don't double the work, you quadruple it. That kind of scaling just makes it wildly inefficient.
And to put a number on that, a pretty standard 4096-point signal would force a computer to perform over 16 million separate operations. Back in the age of vacuum tubes and punch cards, this wasn't just slow, it was impossible. It made real-time signal processing a total fantasy. The math was there, but it just wasn't practical.
So, what changed? What could possibly light a fire under everyone to solve this thing? Well, as it so often happens with these huge technological leaps, the answer was the intense, high-stakes pressure of the Cold War.
After the 1963 Test Ban Treaty, both the US and the Soviet Union agreed to stop testing nuclear weapons in the atmosphere and move them underground. This created a massive national security problem. How do you know the other side is actually following the rules? The only way was to listen to the Earth itself with incredibly sensitive sensors. These things generated these enormous rivers of data, and the goal was to sift through all of it to find the specific signature of a nuke and tell it apart from a plain old earthquake.
All of a sudden, this abstract math problem wasn't so abstract anymore. It was a matter of national security. That dream of fast signal processing, it had to become a reality. And it had to happen, like, yesterday.
And that intense, urgent need, it finally led to the solution. A complete paradigm shift in computing that we now call the n-log n revolution.
The breakthrough finally came in 1965. And it didn't come from some secret government lab, but from a collaboration between James Cooley at IBM and a brilliant statistician from Princeton named John Tukey. Tukey basically suggested this clever mathematical shortcut to Cooley, who then tried it out on an IBM mainframe. The paper they published, well, it would go on to change everything.
They called it the Fast Fourier Transform, or FFT. And look, this wasn't just a small improvement, it was a completely different way of thinking. It took the computational complexity from that brutal n² curve down to a much, much gentler slope called n log n.
The difference in speed was just astronomical. I mean, look at this. For that same 4096-point signal that needed 16 million operations with the old DFT, the FFT needed only about 49,000. That's not a small jump, that's a speed up of over 300 times. And the crazier part is, the bigger the dataset gets, the more insane the advantage becomes.
What this logarithmic collapse meant in the real world was that tasks that used to take hours and hours of expensive mainframe time could now be done in just a few seconds. That bottleneck we talked about, it was completely and totally shattered.
So, how does it pull off this magic trick? Well, the FFT uses this classic strategy called divide and conquer. It just keeps breaking a big, nasty problem into smaller and smaller, much more manageable ones. It splits the data into even and odd samples, solves those simple little problems, and then, this is the brilliant part, it cleverly recombines the results, reusing calculations instead of doing them over and over. That's what cuts out all the redundant work.
Now, with this incredible new speed, a whole universe of applications just exploded into existence. The FFT was about to do way more than just listen for earthquakes. It was about to give sight to sound.
Okay, take military radar. The old, huge problem was trying to spot a fast, low-flying jet against all the noisy background junk, or clutter, from the ground. But with the FFT, a radar system could instantly analyze the signal bouncing back. All that ground clutter, it just shows up at the center frequency. But the moving jet, it pops out as a sharp, distinct spike somewhere else on the spectrum. That's thanks to the Doppler shift. You know, the same thing that makes an ambulance siren sound different when it's coming towards you versus going away. This simple trick enabled look-down, shoot-down radar for the very first time.
And it did the exact same thing for sonar. The ocean is an incredibly loud, chaotic place. But by applying the FFT, a sonar operator could basically untangle that mess of sound and pick out the very specific acoustic fingerprint of an enemy sub, like the 60 Hz hum of its power generator, or the unique whine of its propeller, from miles and miles away.
The impact was just so profound. As one expert put it, the FFT effectively gave eyes to the blind. It turned invisible waves and unheard sounds into a clear visual map you could actually use.
But the story of this modern, world-changing algorithm has one last, absolutely unbelievable twist. Turns out, it wasn't new at all. It was an algorithm that had been rediscovered.
Yeah, so decades after the FFT paper came out, historians dug something up. The legendary mathematician Carl Friedrich Gauss, he had figured out the exact same method way back in 1805. He was using it to calculate the orbits of asteroids. He wrote it all down in a Latin notebook, where it just sat, mostly forgotten, until Cooley and Tukey independently came up with the same idea 160 years later. No way.
You know, when you think back to some of the most iconic pieces of tech from the last few decades, I mean, the gadgets that completely changed how we live, how we listen, and how we talk to each other, they all seem so different, right? But what if I told you they all shared a secret, a kind of invisible engine that was powering the entire digital age?
It all really starts here, with the compact disc player, which came out way back in 1982. For most people, this was it. This was the very first taste of a digital product, promising perfect sound forever, and honestly, it kicked off a revolution in how we all thought about music.
And then, boom, the mobile phone shows up. Remember those legendary brick phones from the 90s? All of a sudden, we were untethered. You could talk to anyone from anywhere. Communication was just never going to be the same again.
And of course, you can't forget the MP3 player. In the late 90s, this little thing let us stuff our entire music libraries right into our pockets. It was really the birth of portable, digital music as we know it, all happening thanks to the rise of the internet. Okay, so you have a CD player, a mobile phone, and an MP3 player. 3 totally revolutionary devices from 3 different decades. What in the world is the connection? What's the hidden engine that was the driving force behind every single one of them?
Well, the answer is this little marvel, the digital signal processor, or what everyone just calls a DSP. It's a special kind of microchip, a piece of silicon that literally thinks in the language of sound waves, radio waves, and images. It is, without a doubt, the true unsung hero of the digital revolution.
But hold on a second. Don't all computers have a brain? You know, a CPU? Why did we need a whole new kind of chip? Well, it turns out your standard central processing unit is a generalist. It's great at logic and control, like running your operating system. But it was never built for the kind of relentless, high-speed math you need to process real-world signals.
And at the heart of the problem is this one key operation that pretty much all DSP algorithms depend on: multiply, accumulate. It just means you take a number, multiply it by another, and add that result to a running total. Sounds simple, right? But to process something like real-time audio, you have to do that millions of times every single second without fail. For a typical CPU back then, that was, well, it was practically impossible. So this really highlights a huge difference in design philosophy. A CPU would take multiple clock cycles, kind of like its internal heartbeats, just to do one multiplication. A DSP, though, it was a specialist. It had a dedicated piece of hardware, a circuit built for one job, to do that multiply-accumulate operation in a single lightning-fast cycle. And the DSP had another secret weapon, its internal architecture. See, most CPUs use something called a von Neumann architecture. Think of it like a single-lane road where both instructions and data have to travel, creating this massive traffic jam. But DSPs, they used a Harvard architecture. It was like giving instructions and data their own separate multi-lane superhighways. This let the chip grab the next command and the data it needed at the exact same time. It was just so much more efficient.
Now, this new kind of chip first showed up inside Bell Labs in '79, but the real game changer landed in 1982. That was the Texas Instruments TMS 3010. You can think of it as the Model T of DSPs. It was affordable, it was powerful, and it unleashed this specialized math power onto the mass market for the very first time. And its first big test? The compact disc.
That's right, the first major battleground for the DSP was the CD. Now, even though the CD was a joint project between Sony and Philips, there was this technical war brewing behind the scenes. And it was a battle that wouldn't be won by better hardware, but by a really clever math trick.
So here's the problem. There was a hardware gap. Sony had a superior 16-bit digital to analog converter. That's the chip that turns all the ones and zeros back into sound. Philips, on the other hand, was stuck with a weaker 14-bit version. Now, in the digital world, that 2-bit difference is huge. It gives Sony's hardware 4 times the resolution. It really seemed like Philips was just destined to launch an inferior product.
But the engineers at Philips fought back with software. They used a DSP to pull off a trick called oversampling. What they did was feed their 14-bit converter data 4 times faster than normal. Now this spread all the unwanted digital noise out over a much wider frequency range. Then the DSP acted like a surgical tool, using a digital filter to slice off all the noise that was way outside the range of human hearing. And the result? In the audible range, their 14-bit player achieved the exact same sound quality as a true 16-bit system. It was the ultimate proof that smart processing could beat brute force hardware.
But the DSP had another job, and this one was even more important. See, digital data is incredibly fragile. A tiny scratch on a CD isn't just a little pop, it's a catastrophe. It can wipe out megabytes of data, and without a way to fix that, the entire CD format would have been totally useless.
This is where the DSP really becomes a hero. It is constantly running this unbelievably complex error correction algorithm. The data on a CD is actually scattered across the disk on purpose. So when the DSP reads this jumbled data, it can identify any missing pieces that were caused by a scratch. Then it uses extra redundant data called parity bits to mathematically reconstruct the lost music perfectly in real time. Seriously, your CD player is literally solving a massive system of equations every second you're listening to it.
So the DSP saved our music. Pretty cool. But its next job was even bigger, putting a reliable phone into everyone's pocket. This was the huge challenge of the second generation, or 2G, digital mobile phone network, the one we all came to know as GSM.
The central problem was the radio spectrum. There's just only so much of it to go around. The old analog 1G networks gave every single caller their own dedicated frequency, which was just incredibly inefficient. To make mobile phones a true mass-market product, engineers had to figure out a way to fit way more users into the same amount of bandwidth.
The solution, you guessed it, was data compression, all powered by a DSP. Instead of sending the actual sound of your voice over the air, the DSP in your phone did something absolutely amazing. It analyzed your speech to create a mathematical model of your vocal tract, basically the shape of your throat and mouth. And then it only sent those tiny, compact parameters over the network. The phone on the other end would then use its own DSP to synthesize a voice based on that model.
And this technique, called linear predictive coding, absolutely crushed the data rate of a human voice, taking it from 64 kilobits per second all the way down to just 13. This staggering reduction is what allowed the network operators to pack 5 times more users onto their networks. That little DSP inside those iconic brick phones was the engine that made the entire mobile revolution possible.
So from CDs to cell phones, the DSP was already a star. But its final act in the 20th century was maybe its most famous of all. It gave us music on the internet and created the MP3.
Back in the days of dial-up modems, trying to send a raw audio file from a CD was just impossible. The MP3 standard solves this with a new kind of lossy compression. Using what's called a psychoacoustic model, the DSP basically acts like an audio magician. It analyzes the music and identifies sounds that are going to be masked by other, louder sounds. So for example, your ear literally can't perceive a quiet flute note right after a loud cymbal crash. The DSP knows this and it just throws that invisible sound away. And the result of all this trickery? A mind-blowing 90% reduction in file size. This, right here, is what made music sharing on the internet possible. It's what fueled the creation of the iPod and the entire portable digital music industry. All thanks to a DSP running a clever psychological trick.
Now, over time, the industry kind of split into 2 main flavors of DSPs. You had fixed-point chips, which were the workhorses, fast, cheap, and super power efficient. They were perfect for things like mobile phones. And then you had floating-point chips. These were the thoroughbreds, more expensive, more power-hungry, but with a massive dynamic range that was perfect for high-end stuff like professional audio or military radar.
So really, when you step back and look at it, the story of the DSP is pretty remarkable. It's the story of how decades of abstract mathematical theory about signals and information were finally captured, perfected, and literally etched into a tiny piece of silicon that we could mass produce by the millions.
We're going to dive into one of the biggest shifts. It's this move from processing signals with, actual physical circuits to something that feels a whole lot more like machine intuition. It's a journey that really explains how our world got so smart, so incredibly fast.
And you might think, oh, it's just faster computers running smarter code. And, you're not wrong, but that's only a tiny piece of the puzzle. Something much bigger has changed underneath it all.
Back in the 20th century, if you had a radio, its purpose was physically baked into it. Its function and its hardware were one and the same. If you wanted that radio to change from, say, receiving AM to FM, you couldn't just download an update. Nope. You had to get out a soldering iron and physically rebuild the whole circuit. But then, the first great abstraction happened. The big idea here was something called software-defined radio, or SDR. And it was a pretty radical thought. What if the hardware was just a generic kind of dumb pipe that just grabs a huge slice of the radio spectrum, and all the smart stuff, the tuner, the filter, all of it, what if that was just lines of code? And this idea was actually kicked off by the US military. See, they had this logistical nightmare, dozens of different radios that couldn't talk to each other. So back in the 90s, they started Project Speakeasy. The goal, build one single box that could become any radio, just by loading new software. Now the first one filled the entire back of a truck, but it worked. It proved the concept was possible.
And just like that, the identity of the device wasn't in its wires and circuits anymore. It was in the software. The radio had become code. This was the first revolution. But, making software do the heavy lifting of physical hardware, well, that required a whole new kind of engine.
Of course, you can't just run this stuff on a pocket calculator. It needed incredible processing power. It started with these special chips called digital signal processors, the workhorses. Then came FPGAs, which are like these amazing digital chameleons, chips you can totally reconfigure on the fly, perfect for stuff like 5G. And finally, believe it or not, the GPUs that were built for video games turned out to be absolute beasts at this kind of work, becoming mini supercomputers for things like advanced radar.
And all that hardware horsepower brings us to the second, and honestly, way more disruptive revolution. We went from hardware to software written by people. But now we're moving from software written by people to algorithms learned by machines.
You have to understand, for decades, signal processing was a painstaking, handcrafted art. To get a computer to see an edge in a picture, engineers would literally spend years designing these complex math filters. The new way? You just show a neural network millions of pictures, and it figures out its own filters. It learns what's important all by itself. It develops its own kind of visual intuition.
And if you want to put a date on when the world really changed, it was 2012. A neural network called AlexNet didn't just win a huge image recognition competition, it absolutely demolished the competition. It proved once and for all that this new data-first approach was just flat out better.
And this totally flipped the script on what it means to be an engineer. Your job was no longer to design the perfect solution. Your job was now to design the perfect learner that could go and find the solution on its own. You're not building the pipeline anymore. You're building the architecture that learns the pipeline. It's a whole new level of abstraction.
So this all sounds a little abstract, right? What does this actually look and sound like in the real world? Well, the results are kind of stunning. They create sounds and signals that are just fundamentally different from anything that came before. Remember those old robotic voices from the first GPS systems? They sounded like that for a reason. They were based on a really simplified mathematical idea of a human voice, a model from the 1960s. Yeah, you could understand them, but they had zero nuance, zero soul.
But now, a model like WaveNet has no idea what a human vocal tract is. It doesn't care. It just listens to thousands of hours of real audio and learns, moment by moment, to predict the next tiny piece of the sound wave. And by doing that, it picks up everything. The breaths, the little lip smacks, all the tiny imperfections that make a voice sound truly human. And this exact same revolution is happening with invisible radio waves. We're now using AI to pull clean signals out of noisy, distorted messes, far better than any traditional math could. What's even crazier is that some researchers think future 6G networks will have the transmitter and receiver be two halves of the same neural network, working together to learn the absolute best way to talk to each other in any environment.
Just let that sink in for a minute. This isn't just about making our current methods better. This is about letting machines invent entirely new languages of radio waves on the fly, languages that are totally alien to us, but perfectly designed for that exact moment in time.
So, what does this all add up to? What's the big picture here? This isn't just a change in technology. It's really a change in philosophy. It's a brand new way of thinking about science and discovery itself. For the better part of a century, signal processing was what you'd call a deductive science. You'd start with first principles, physics, mathematics, and you would deduce an elegant solution. We are now charging headfirst into an inductive era. We start with just insane amounts of data, and we let the machine induce the solution from the patterns it finds inside.
And really, if you take one thing away from all of this, let it be this. The first digital revolution was about turning the signal, the world, into ones and zeros. This new neural revolution, this is about digitizing the process of discovery itself. It's digitizing intuition.
Which leaves us with one kind of mind-bending question to chew on. We've built these incredible tools to see the world for us, not based on our rules, but on the raw, unfiltered data of reality. So, as they learn to interpret the world on their own terms, what will they see that we can't? What patterns, what secrets have been hidden in the noise, invisible to us all along?